Good morning, everyone. This is Mr. Couple. I'm here today with my IBHL Year 1 students, and we're going to be talking about Coulomb's law and electric fields. If you haven't yet downloaded the handout, please make sure you go to Google Classroom before you watch this video and download the handout. It looks like this. You can go download it and follow along with me as I do the video. I've got a couple of people on voice chat. I know Braden's here and Kong's here, so I'm probably going to be asking them to jump in. I think Alberto's listening as well. If you guys want to jump in at any time, feel free. All right, let's begin. So first off, we're going to talk about uh, a static configuration of charge. So static means that the charges aren't moving. So these two charges, Q1 and Q2, they're fixed in place. What it's telling us is that they're 50 centimeters apart, and it's going to tell us how much charge they have. So Q1 has a positive 30 microcoulomb charge, and Q2 is a positive 10 microcoulomb charge. Let's see if I can move this a little bit more. Whatever. Okay, so what we're going to try to do now is figure out the answer to this question. So here we have Q1, which is 30 microcoulombs. That is not what I wanted to draw with. 30 microcoulombs. And Q2, which is 10 microcoulombs. Now, the reason I'm using microcoulombs is because this is what you would normally have, like if you took a balloon and you like rubbed it on your hair and charged up the balloon, you'd have about a microcoulomb-ish of charge on there. And so I was trying to use some like human-sized charges that you'd be familiar with, like if you scuffed your feet against the carpet or something like that. And so about microcoulomb is usually what you're expecting there. And then we're looking at about 50 centimeters, which is like half a meter apart. So we're going to try to calculate eventually the force that they're exerting on each other. But first, I want to ask you guys, these two objects are going to repel each other because they're both positively charged. But my question is, which object has a greater force on it? So we've got this big 30 microcoulomb charge and this little 10 microcoulomb charge. So my first question for you guys is, which object has a greater force exerted on it? So what are your thoughts about that?
Wouldn't it be object 2 because object 1 has a greater amount of energy, so it would cause a greater amount of force?
Okay, that's one thought. So this is a lot larger object, the 30 microcoulombs, so it's going to have a greater effect on the smaller object. Thank you, Braden. Anyone else want to say anything? Thoughts? Okay, so we have to think of this exactly like we would think about any interaction between two bodies. So what we have here is there's interaction. So these objects are interacting. And so what do you know about the force that's exerted between two objects that are interacting with each other? Force is just a result of an interaction between two objects. And so what do we know about the force that the objects during an interaction exert on each other?
Do you mean like F equals ma?
Well, that's the how you convert from force to acceleration. I'm just asking about if we have two objects that are interacting with each other, how do the force that they exert on each other compare?
Equal?
Yeah, it's always equal. What law is that?
First law?
Where
Isn't that third law?
Yeah, it's third law. So Newton's third law says the forces they exert on each other are equal and opposite. I'll just say equal in magnitude, since that answers the question. So, Braden, don't feel bad about what you did because everybody does that. You think, oh, there's this big honking charge, so it's going to just like push the crap out of anything around it. Like it is true that this 30 microcoulomb charge is going to be capable of providing more energy to another charge around it. But the question was, which one has a greater force on it? And when two objects are interacting, so object one is pushing object two to the right, and object two is pushing object one to the left, that interaction has to be the same. There's no other possibility of why the forces have to be the same. That's just Newton's third law. So hopefully that makes sense. So you can see why I'm starting with this misconception, because this is a common mistake that people make is you think, oh, the bigger charge is going to exert a stronger force on the smaller charge. That is not at all how electricity works. Okay, so now what we want to do is we want to actually calculate the strength of that force. So there's this law of physics, it's called Coulomb's law. So Coulomb's law says I'm going to take off my keyboard. Okay, so Coulomb's law says F equals K times Q1 Q2 over R squared. So this was in the video that we watched last time for the lesson. And this is called Coulomb's law. The way Coulomb's law works is you just take the two charges. So you take the Coulomb is the unit of charge. It's named after Coulomb. So you take the two charges and you multiply their charges together, and then you divide by the square of the distance between the two charges. And then you just have to take that and multiply it by this constant, which is called Coulomb's constant, which is a K. You could look that up in the data booklet. It's 8.99 times 10 to the ninth. And then it has a really complicated unit. It's Newton meters squared per Coulomb squared. So it has this really crazy unit, and you'll see why it has such a weird unit in a moment when I actually solve out the rest of this problem. All right, so let's do this now. So what we have to do is we have to take k, q1, q2, multiply all those together, and then divide by the square of the distance. And we have everything that we need to solve this. So we're going to start by writing 8.99 times 10 to the 9, and I'll put the units here, Newton meters squared per Coulomb squared. I just want to put the units there because it'll help us to see how this equation works out in the end. Then we're going to multiply by the charge of Q1, which was positive 30 times 10 to the negative 6 coulombs. Where did the negative 6 come from, you guys?
The what is it, micro?
Yeah, it was the microcoulomb. And then we have one more charge, which is positive 10 microcoulombs. And we're going to divide all of that by the distance between them. So they were 50 centimeters apart. So how do I need to write that?
50 times 10 to the negative 2.
50 times 10 to the negative 2, or there's an easier way of writing it, which is 0.05. Okay, before we start evaluating this with the calculator, I want to actually go through and look at the units. So the first thing you notice is that the meters squared in the Coulomb's constant are going to cancel with the meters squared on the bottom. So those meter squareds are going to cancel. You can notice over here when we look at the charges that you have coulombs times coulombs, and so those are also going to cancel out with the constant inside, with the unit inside the constant. So the coulombs are going to cancel out. And so look at what we're left with. The unit that we're left with is just newtons, which is what we needed because we're trying to find the force. So that works out beautifully. And so that's why the units on that Coulomb's constant are so bizarre because they have to cancel out in this equation, giving you newtons in the end. Okay, so now we just have to grab our calculator and start plugging in these numbers. So 8.99 times 10 to the ninth power multiplied by 30 times 10 to the negative 6 multiplied by 10 times 10 to the negative 6. And then all of that's going to be divided by 0.5 squared. And so I get 10.788. And so I say, let's just do it to 2 sig figs. So we can say that the force is about 11 newtons. So one thing to realize by working out this problem is that when you have microcoulombs of charge, and this is just a helpful thing to know about, if you have microcoulombs of charge separated by about a meter-ish distance, you're going to end up getting newtons of charge, like not like micronewtons or millinewtons or meganewtons. So like microcoulombs give you forces around, 10-ish newtons. So keep that in mind when you're solving problems like this. So what if instead these charges were nanocoulombs? Well, then you would get a much, much lower force than a newton. Or what if these charges were instead, um, you know, a kilometer apart? Well, then you get a much, much, much lower force. And so just kind of keep that in mind. Like microcoulombs is like the pretty standard force that or standard unit of charge that you're going to see for everyday situations like scuffing your feet against the carpet or rubbing a balloon on your hair. Okay, let's look at number part B. So a positive test charge, we're going to place a positive test charge. And so what I mean by that is like, it's not really a charge, like it's kind of just an imaginary charge. So I'm just going to call it positive Q. It's a really, really small charge. So it's not really going to have any effect on the charges that are already there. We're just going to kind of use it to like probe in and like see what's going on there. Like what would happen to that imaginary charge if we placed it in that location? What would these other charges do to it? All right, so the question says positive test charge Q is released from rest at the midpoint between the two charged objects. In which direction will the positive test charge move? So, what are your thoughts on that, guys?
Stationary.
So, it'll stay put. Why do you think it's going to stay put, Alberto?
The two charged objects keep it in place.
Yeah,
It's positive.
so Q1 would push it to the right, and then Q2 would push it to the left. Since they're both positive, they're going to repel each other. So you'd have a force pushing it to the right and a force pushing to the left, and so they would cancel out and it would stay put. What do you guys think about that? Because there's a flaw in the reasoning there,
They're not equal in magnitude.
right? The charges aren't equal. So there's a larger charge on the left, which means that that force to the right, the repelling force from that Q1 is going to be much greater than the repelling force from Q2. Do you guys see that? So this
Yeah.
is the force from Q. This is the force from Q1, and then this is the force from Q2. And so we can see that F1 is going to exceed F2. They're both the same distance apart. So if we think about Coulomb's law, so Coulomb's law says F equals KQ1, or I'm going to put it as, I'm going to write it a little bit differently. I'm going to write it as big Q, little q. Oh my gosh, I'm having a really hard, it's like way low down on my screen. Let me do this. Okay, so I'm going to write it like that. And so what I'm doing there is that this little q, the reason I wrote it as little q is because that was our test charge. And so what we're going to realize is that what's changing is the big Q. So here you have this as the big Q, and over here you have this as the big Q. But our little q is staying the same. So what's happening is you're going to have the same distance, the same Coulomb's constant. That's not going to change. But if you have a bigger charge, you're going to end up having a greater force. And so that means that our charge is going to actually move to the right. And then we just need to explain why that's going to happen. Why can't I draw a straight line? So we just want to try to explain why that happens. So we'll say they're equal distance. So test charge is the same distance from both charges. It will be repelled more strongly. I'm running out of space. It's because I wrote the equation by the larger charge. Okay, so now we're going to solve this absolutely insane problem. So you can imagine that if we move that test charge, if we moved it around, that there would be a location where what Alberto thought would actually happen. So you can imagine that what would happen as I move this Q, as I move it to the left, what would happen? I'm sorry, not to the left, to the right. What would happen as I moved it to the right? So what would that do to F1?
Shorten.
It would shorten it because we're getting further away. The distance between the big blue charge and test charge is going to get increased. So there'll be a less force. And as we get closer to the green Q2, our F2 is going to get larger. So we imagine that there's probably a location like around here where the forces are equal, that the force on F1 and F2 are the same. And we want to figure out what is that distance. So we want to figure out how far away from how far do we need to go to get to that point? So here's what I'm going to do. I'm going to erase all this because it's kind of crazy right now. I'm going to put where we think the charge is going to be. We think it's going to be about there. And at this location, the force from charge 1 and the force from charge 2 will be equal on our object. And we want to figure out what that distance is. So I'm going to call this, let me use a straight line tool. So we'll call that distance from Q1 to there. We'll call that distance D because we've already defined that this distance is, we've already been using this as R. So we want to figure out where do we need to stick that Q? Where do we need to stick our positive test charge so that there's no force on it? We want to figure out where the net force is 0. So if the net force is 0, then that means that F1 and F2 are going to be equal to each other. So let's do that. Okay, so first of all, this is F2, and then this interaction is F1. So the first thing that gets confusing is like it's the little charge interacting with the two other charges. So let's start drawing out the equation for that. So to solve this problem, we want to know when does F1 equal F2? And so now we're going to substitute in Coulomb's law for that. So we're going to say K, Q, actually I'm not going to use big Q, I'm going to use little q. So Q1 times little q. Whoops. So what I'm doing here is I'm doing, oh my God, I cannot draw a Q. I'm doing the interaction between these two charges, between Q1 and Q. So I'm looking at the interaction between Q1 and little q. So how far apart are Q1 and little q? The distance between them. So these guys are distance d apart. So I'm going to divide by the distance squared. Well, what the heck did I just do? No idea what I'm doing here. All right, that's fine. I'm going to divide by d squared. And that's going to be equal to k q2 times q over, and then we have the other two charges. So this is q2 and little q. And so how far apart are they? So that distance, that's a little bit more tricky to find. Any ideas, guys? What are your thoughts on what that distance is?
R minus D.
Yeah, that's r minus d. So coming back down here, I'm going to put r minus d, and then I have to take that whole thing and square it. So this is a very complicated question. Like this is probably like the hardest variation of these types of problems that you'll see. And I just thought I'd show it to you guys on this video. Okay, now let's solve it. So k's are going to cancel out because we got k on both sides. We also have the same little q on both sides. This is why our little test charge didn't matter. It didn't matter that it was what charge it had. It was just an imaginary charge because its charge is going to cancel out anyway. We know what q1 is. So q1, let's just substitute in what q1 was. So that's 30 microcoulombs divided by distance d, which we do not know what it is. And over here, Q2, well, Q2 was 10 microcoulombs divided by R, which was 0.5 minus d quantity squared. You can see that the microcoulombs are going to cancel out, and we just have to solve for d. And then this is just a complicated algebra problem. So the first thing I'll do is I'll just move the denominators to the opposite sides. We'll just multiply them over. So we're going to end up with 30. My camera is getting in the way. Let me move it over there. Oh, geez, I don't want to see my face that big. All right, so we're going to have 30 times 0.5 minus d squared, and that's going to be equal to 10 d squared. I think I'm just going to get rid of my face. Yeah, I'm tired of looking at myself. All right, so you know what? I'm just not going to write these. You know, what I just noticed there is if I divide both sides by 10, I basically don't need to even write. I could just write the 3 like that. Okay, now the next thing is we want to solve for d. So the easiest thing to do at this juncture would be to just take the square root of both sides. So then that'll end up with root 3 times 0.5 minus d equals to d. Okay, so now I'm going to have to put the root 3, I'm going to have to distribute it through here. So we're going to have half of root 3, so 0.5 root 3 minus root 3d is equal to d. So I'm going to need to add the root 3d to the other side. So d plus root 3d equals to 0.5 root 3. Okay, almost done. And so now I'm going to have to factor out this d from over here. So I'm going to end up with d is going to be equal to 0.5 square root of 3 divided by, after I factor out the d there, we're going to have 1 plus root 3. So now this crazy thing is what we need to throw into our calculator. So let's do that. I guess I could put my camera back up there now. Okay, so here we go. So 0.5 times square root of 3. I think that's how you do square root. Yeah, there it is. Okay, that's 0.5, and then I'm going to, that's half the square root of 3 divided by 1 plus the square root of 3. So I got 0.3169, which seems like it's completely the wrong answer. Oh, there's clearly a mistake here somewhere, and I have no idea where it is.
No, wouldn't that be plausible because that's in meters, not centimeters?
Oh my God, I'm so dumb. That's exactly right. Yeah, this is perfect. Okay, cool. So what would be the middle of the two? I don't know why I didn't think this through. What would be it's because the answer on my paper was wrong. This one's correct. So what would be the middle point here? How far would it be if that was D? If D was at the middle, then that would be halfway, right? So it'd be 0.25. And so we're past that. So yeah, we're at 0.32. So this is perfect. This is exactly what we wanted. Saved. Jeez, I thought I did it wrong and I didn't. All right, how much time do I have? Oh my gosh, I'm like running out of time here. Okay, so that's a really hard problem. I've seen this on IB exams in the past. It pops up from time to time, but there you go. Okay, let's talk about electric fields. This part's really simple. So I'm going to leave most of this for you guys to read since you're going to have this handout and print it out. But the basic idea is this. How the heck can two charges push each other when they're not touching each other? Like how does this charge, like let's call this guy Q1 and we'll call this guy Q2. Like how does Q2 know that Q21 is over there? Like they're not touching each other. It's not like a force typical like getting like smacked or something like that. Like where there's contact. Like how do the charges know that the other charge is there? And how do they know that they need to get pushed apart from each other? Like this is a really weird philosophical question that confused physicists for a really long time. Like when Isaac Newton first came up with his theory of gravity, this actually perplexed him. Is like, how could the Earth be pulling the moon from such a great distance? So to solve this problem, physicists came up with this idea called the field. In this case, it'd be the electric field. So what we say is two facts that you need to know is that charged objects, so this is the first fact here at the top, is charged objects create electric fields in the space around them. And the second thing you need to know is that charged objects feel a force from the electric fields created by other charges. So let's explain how this little q over here, how does it know to get pushed? How does it know to move to the right? So here's a little concept map that I came up with to try to explain this to you guys. So the first thing we do is we say, all right, there's this charge over here. So I'm going to write electric charge in this box. And so now what do electric charges do? Well, electric charges create these things. Electric charges create electric fields. So they're going to say create electric charges, I'll say. Electric charges create electric fields. And then what do electric fields do? Well, electric fields exert force on other charges that are in the field. So how does this charge know to feel a force? Well, because the electric field is telling it. The electric field is over here, and that charge is interacting with the electric field. And so that's how it knows where to go. It knows to get pushed away from the positive charge because the field is telling it where to go. So the idea is that charges, they send out these electric fields, and they send them out in all directions, and they go to an infinite distance away from the object. And so that's our concept, is that electric charges create electric fields. That's the first idea. Electric charges create electric fields. And then the second idea is that charged objects feel a force from the electric field. So the electric field is on charges. So that's our concept map for understanding electric fields, this concept of electric fields. I don't remember if the video talked about electric fields or not, but there it is. Okay, let's talk about this mathematically now. So we've got symbols here. We got Q, we got, let me erase all my colors. We got big Q, we got little q, and the only thing missing is the distance. So I'm going to label come on, erase. Why aren't you erasing? There, okay. So I'm going to label the distance between these guys. So starting at the center to the other center. And so we're going to call that distance r. And the reason we use r is because you can imagine it can be radially anywhere. These two objects could be separated by any radius. I mean, it could even be like a spherical radius. So that's why we use r for that. Okay, so the electric field is this idea. So E is the symbol for the electric field. The electric field is defined as the force per unit of charge. Well, here's the thing. We already know what the force is. The force between these two charges is going to be Coulomb's law. It's going to be K, big Q, little q. I failed to draw that little q. Big Q, little q over r squared. And then if we divide by the charge, which is what the definition of the electric field says, it's what the definition I was reading from off here. The definition of the electric field is to take the force and divide out the little q. So what this ends up doing is it just gets rid of the thing that's in the field. And then we're left with this equation, E equals to K, big Q, over r squared. And that's the equation for an electric field. So this is the electric field equation, or electric field strength. But that's just the field between two, that one charge creates. So you can imagine if there's another charge, you're going to have to run this equation for however many charges you have and then add them all up. So we're just looking at one charge and what it does. So the thing that I always like to tell students is that to make an electric field, you only need one charge. But to make an electric force, like up here, to make an electric force, you need two charges. So to make an electric force, you need two charges to interact with each other. But to make an electric field, you only need one charge. And that's what this equation is showing us. One charge makes one electric field. So now what we're going to do is we're going to rewrite Coulomb's law by using this new substitution. So F equals to K Q. I'm going to do it with big Q, little q. So K, big Q is the first charge, little q is the second charge, divided by r squared. And so what you'll notice is that K, Q over r squared in Coulomb's law, that's just the electric force. So we can write down that F, I'm sorry, not the electric force, the electric field. We can write down F equals to E times Q. And this is super simple. Like this equation is crazy, crazy, crazy easy. And then what's really cool about this is that we actually did this with gravity. You guys just never realized it. So when we wrote down F equals GM, well, actually we wrote it as mg, but I'm writing it this way so the order matches up. G is just the strength of the Earth's gravitational field, where the Earth's gravitational field is the strength of 9.81 newtons per kilogram. Down here, we're using the strength of the electric field. So these equations look very similar, and it's not by accident. It's because electric fields and gravitational fields they behave very similar to each other. We'll talk more about gravity in an upcoming unit. Okay, let's finish this because I'm out of time. I'm way out of time. So I just want to finish this up. So here's a picture. We have two charges that are placed in an electric field. This electric field is a uniform electric field. The reason you can tell it's uniform is because the space between the lines is constant everywhere. The spacings between the field lines tell you the field strength. It says which object has a stronger force exerted on it. So we've got object A, which is 2 coulombs of charge, and object B, which is 10 coulombs of charge. So which object is going to have a larger force exerted on it? Well, we could look at the equation that we just derived. F equals EQ. Actually, it's usually written as QE, charge times E. I don't know which way you want to do it. I like doing it this way because then you can say it FEC. I just think that's funny. So I'm going to do it that way. But I think the data booklet does it the other way around, but it doesn't matter since the order that you multiply numbers in isn't relevant. Okay, so they're both in the same electric field. And so the one with the stronger force then is obviously the one that has a greater charge. And so which one has a greater charge? Let's object B. The field exerts a force of 10 newtons on object A. Okay, so now they're telling us a little bit about the field. So there's 10 newtons on object A. So the field exerts a force on charges that are in it. So there's going to be a force here of 10 newtons. So then we want to calculate from that what the field strength is. So the field strength is going to be the force per charge. So we know that we had 10 newtons on 2 coulombs. So from that, we get that the field strength is 5 newtons per coulomb. So this field exerts 5 newtons for every coulomb of charge that's placed in the field. So this is a way of saying like, hey, we'll tell you how your charge will behave if it's put in this field. It will get 5 newtons of force for every coulomb of charge the object has. And so that's why we define the electric field this way, so that the charge of the object in the field doesn't affect the strength of the field, but it will affect the force that it feels from the field. And then lastly, we want to figure out, determine the force exerted on object B. So force is equal to electric field strength times the charge. So we just found out the field strength was 5 newtons per coulomb. And then we're going to multiply it by our object B, which has 10 coulombs. And then you can see that the coulombs will cancel out here. The per coulomb and the coulombs cancels, and we just get that the force exerted on it is 50 newtons. Super easy stuff. And then we can see that that's an agreement, that there's a 50 Newton force on this guy. And that, yes, we were right, object B has a stronger force. All right, so that's it for this video, guys. Sorry it went a little over time, but yeah, so we're going to be continuing next time by talking about electric currents and doing a whole bunch more mathematics. I'm probably going to keep doing this handout format just because it's easier for me to do math, and I just feel it's easier for you guys to follow along as well. All right, have a great day. I'll talk to you later.